Hey everyone, my name is Johan Uruti. I'm the Director of Operations and Technology for Spartakus Technologies, and very happy to have you with us today. The purpose of this presentation is about how to perform PM optimization and minimize downtime. And I'm very happy to have Alain Pellegrino with me today. Alain is the President of Reliability Solutions, and actually we've been working together for a few years, and this is how I learned pretty much everything there is to know about PM optimization. So Alain, do you want to introduce yourself?
Sure. Hello, everyone. I see a lot of familiar faces, so it's very happy to see you all. So I'm the president of Reliability Solutions. I've spent last 20 years at Laurentide Control as the VP for Industrial Reliability Solutions, and I'm CMRP, and very excited to talk about PM optimization today.
On my end, I've met Alain at Laurentide Controls, and we've done a lot of PM optimization projects together, and we've built that kind of knowledge and recipe, and we're going to share those best practices we've learned through time throughout this presentation. For those who don't know Spartakus Technologies, we are a company based in Montreal, Canada, and we are partners in reliability engineering with a lot of experience. We have a software, Spartakus APM, that is used quite extensively in North America. We have more than 2,000 plant sites, manufacturing sites that use our software. And we also offer a range of reliability services such as PM optimization and all of these big reliability kind of projects, as you can see on this screen. Alain, you want to introduce Reliability Solutions?
Yeah, absolutely. So Reliability Solution is based in Pensacola, Florida, north side of Florida. Where we had snow last week. Anyways, that's something quite interesting. So we have a group of 45 reliability specialists, and we focus our effort improving reliability at site through coaching and training. So we do a lot of training on reliability for maintenance, for precision maintenance, as well as operator care and condition-based monitoring. We also offer services such as quality control and insurance quality of installation of rotating assets and a lot of mentoring. So in a nutshell, that's what we do. Been in business for almost 20 years, 19 years to be exact.
Perfect. Thank you, Alain. So throughout this presentation, we're going to go over some background with regards to PM optimization, why we should do it, and then we're going to talk about how to do it for the most part of this presentation. So we're going to look at the prioritization of efforts and also a bit of the methodology. We've developed some, best practices, and we'll finish with a success story. One of the many success stories that we've had, myself and Alain, over time. So to start this first part, we'd love to start with a poll. And some of you may work in manufacturing sites where the preventive maintenance is not optimized at the moment. So we'd like to do a little bit of a poll that should show up on your screen. And it's a question that we want to know: why haven't you optimized your PMs yet? So if you can answer, we'll see what the results are. You should see the results being updated on the screen. Okay. So I see a lot of lack of resources. More than 50% of the answers revolve around that. Then it's followed by lack of time. So it really appears that if your preventive maintenance program is not as good as you wished, it's because you're lacking in resources and time, which is, I would say, probably most of the answers we get when we do these kind of projects. Very good. Thanks a lot for your answers, and we'll go to the next slide then. Alain.
Yeah, so first thing I'd like to touch on is, why PM optimization and why is it so important? So I took this screenshot from a study done by an organization called Solomon, and basically they do a lot of audits across North America in different industrial plants, and they look at best practices. So they rank each facility that they audit on a scale of 1 to 4, which is the top quartile would be top first, the best performance, and then the lagger in that same industry would be bottom fourth. So if you look here, the top first quartile, they are the best performer. I don't want to go too deep in the details of each, but let me just give you some insight, right? Here, the first two columns here, so the best performer, they are able to have a maintenance spend of 1.7% of their replacement asset value that they own. Compared to the lagger in that same industry, they spend 18% of the replacement asset value every year for maintenance. So you see a big difference between those two types of company, even though they might be running the same type of assets. The other thing I'd like to focus our effort in today, we want to talk about PM optimization. I guess PM optimization, if you look at the percentage of time that is spent by the resources, the maintenance resources to do PMs, for first quartile company, they spent less than 20% of the time of the crew to do preventative maintenance, compared to bottom fourth quartile, where they spend 42% of the time. And in that study, preventative maintenance is it's based on calendar. So it's a calendar-based maintenance strategy. If you look at the best performer in that same industry, where do they spend time? Basically, here is the percentage. I'll use the vibration example. So in 89% of their rotating assets, they do vibration analysis, the first quartile companies. The bottom fourth quartile, they only monitor 3.8% of their asset using predictive technologies. And you could compare all these different condition-based monitoring techniques here, vibration, infrared mechanical, or infrared electrical, or oil analysis. You see they rely heavily on condition-based monitoring to monitor their assets. That's why they don't need as much time to do PM, because they or time-based preventive maintenance, because they rely on condition-based monitoring. Now, that being said, the lagger in that same industry, they don't rely on those techniques. So that's why they need to spend time on preventative or time-based maintenance. But if they would use those predictive technologies, then they would be able to free up some time and spend less time doing non-value added preventative maintenance tasks. Make sense? So, let's see here. So when we talk about defining the maintenance strategy, I think we need to align on on the definition of what we mean by that, right? So basically, the definition of a maintenance strategy is regularly scheduled work performed at prescribed interval, intended to proactively avoid, delay, or detect the on-site of failure. So basically, everything that we do, could be everything that we do in preventative and lubrication practices, or predictive maintenance, or condition-based monitoring, or total productive maintenance, or outside contractor that comes in and do PM work. Are they all intended to proactively either avoid, delay, or detect the on-site of failure? So that's really the questions that we need to ask ourselves. So we want to focus our effort on those failure finding tasks using different technologies, and of course also preventive maintenance in there. So those are all the elements of the maintenance strategies that we want to look at.
Thank you, Alain.
Yeah.
So what we're going to do at the moment is we're going to talk about why preventive maintenance is ineffective and inefficient. So I'm going to give you a scenario that you probably have lived in the past. It starts with an unplanned shutdown due to equipment failure, and you will repair and restart as quickly as possible, and then you're going to sit down with the maintenance planner and say, okay, let's add a PM in our CMMS, quick and dirty, to avoid the repetition of this event. You'll schedule preventive maintenance. You'll stop the machine. You'll do that PM, restart production, but guess what? It will happen again. That failure will happen again, and you'll be trapped into like a doomsday loop of failures. It's because what we've done wrong here is we've added a quick and dirty PM in our system. So I want to, before we go into what good looks like, I want to talk about what bad looks like. And typically what we find is not so good preventive maintenance programs. So the first thing is no preventive maintenance at all. It's not rare that we go to manufacturing sites and we ask, okay, can you give us an insight on what your preventive maintenance looks like? And they actually don't do any PM at all. It might be general on the overall site, or it can be very specific on a couple of assets which are critical, but that happens quite often. I can guarantee you that. Redundancy is also something we see very often. I'm going to give you an example that I've seen at a site I've been to, and it was about drive belts. So the operators would check the drive belts on a weekly basis, so 52 times a year. The mechanics would do it on their monthly shutdown, so 12 times a year. Plus, we would bring contractors every year to inspect the belts, or actually do work on the belt. So that would bring us to a total of 65 annual inspections or intervention on those drive belts, which seems quite intense, right? So yes, that's something we see a lot. Also, something we see a lot is very low value added tasks. If you look at the example here on the right, we have a monthly shutdown PM done by a millwright. And what we can see in there is motor inspection, belt inspection, inspect pulleys, inspect tank, which, if you have a very experienced millwright with a lot of, I would say, responsibility and accountability, he would do a very thorough inspection and he would look for specific types of failures. On the other hand, if you give the same paper to a millwright that has no accountability and doesn't care or is not trained to do the work right, well, he'll just put a check mark and go to the next piece of equipment, right? So no pictures, very, very subjective tasks is also something we see quite often when doing this type of work. Old PMs. So whether it's decommissioned pieces of equipment or old tasks or assets that have changed in the past few years, well, we end up with PMs with data that does not belong there. And finally, this is going to be the central piece of this presentation. It's not based on failure modes, risk, and effects. So we talked about the PM that was added after weekend breakdowns. We could talk about tasks that are added for non-detectable problems or for tasks that are done too frequently for non-critical assets. We're going to talk a lot about that. So really what we want to focus our efforts on is looking for symptoms. This is really the central point of this presentation. So like a doctor, we want to ask our machines, what are the symptoms we want to look for and address those symptoms. And I'm going to, of course, take a very simple human comparison. When you have COVID or a cold or a flu, you're looking for a very specific symptoms, right? Like, for example, a sore throat, runny or stuffy nose, or a cough, you see? And what I've highlighted is symptoms that are common to 3 of these viruses. Should you take a COVID test to identify if it's a flu or COVID, you'll see, right? We're not really talking about the causes, but we must look for specific symptoms to identify the causes of problems. So really, what we want to focus our efforts on in this presentation is the symptoms of the machines. So let's take an example, and let's take a piece of equipment, rotative piece of equipment, and the question I'm going to ask you guys is, what are the failure modes of an electric motor? And to do so, we're going to start another poll, and I want you to type down what you think are the symptoms of failure, upcoming failure of an electric motor. So R1, if you want to put up the poll on the screen, and you'll have the ability to type in whatever answers you want, and we'll look at the results. So again, think in terms of symptoms. What would you look for to identify upcoming failures of an electric motor? Okay. And of course, you can submit multiple answers. Okay, so I see a lot of vibration, overheat, high temperature, amperage, power consumption, noise. Yes, yes, lots of good answers, right? So again, it's really about identifying the symptoms. We're not focusing on the causes, what might have caused these well, symptoms, but really what we can look at, what we can identify. Very good. Yeah, so I see a lot of very, very good answers there, guys. Good job. So there are lots of possible answers there. So, and of course, I don't want to go into too technical in there during that presentation. So let me identify a couple of them. So noisy, overheat, vibration, dirty, lack of lubricant, insulation issues are some of the answers, some of them, okay? Again, we could think of dozens of them. And really the next step is, okay, for each of these failure modes, we need to identify a certain level of risk. Are we going to tackle all of these failure modes or just a portion of them, the ones for which there is a higher risk? To do so, we're going to look at the severity of failure if it's not covered, right? So you can go from very low to moderate to high severity. You can refer to your criticality ranking sheet for that if you have that. And then you'll ask yourself, what is the probability of occurrence of these failure modes? So you look at the history of issues and ask your maintenance people, how many times did we have overheat issue? How many times did we have noisy issue, and so on and so forth, right? So in the end, you end up with a risk matrix, and you'll be able to say, well, this is acceptable, unacceptable, or intolerable, right? And for the rest of this presentation, we're just going to take a very simple example, like the overheat, which was one of the failure modes that you guys identified, and see how we can tackle overheat in a PM optimization process. Before we move on to the PMO process, I want to talk about the failure modes. So failure modes can, have two kind of, can refer to two types of failures. It can be sudden failures or gradual decay. In the case of sudden failures, we're going to have constant mean time between failure or non-constant mean time between failure. If it's constant, then we'll replace before it fails. If it's non-constant, we'll have to have that piece of equipment in stock to replace because there is no chance for us to detect it's the upcoming of this failure. In case of a gradual decay, we'll monitor the condition at optimal intervals. And coming back to overheat, as we said, this is something that we can trend in time, right? The variation and the evolution of temperature can be trended. So this refers to a gradual decay. And talking about gradual decay, you've probably seen the PF curve before. So in terms of a PF curve, and for those who are not familiar with it, let me explain it to you very, very quickly. We're looking at the health of a component through time, and we're estimating the time between a potential failure and the actual functional failure of this component or asset. And of course, through time, there are various symptoms that will happen that will give us clues on the time before it fails. Again, we're focusing on overheat here, and overheat can happen in very close to what we call the reactive domain, especially in rotative assets, right? So maybe it's going to require a shorter interval of inspection, higher frequency of inspection, right? Because it's very close to the to this failure point here. But we'll go back to that later in the presentation. So we've covered the failure modes. We know it's important. Now let's focus on the PMO process and how to prioritize efforts.
So let's talk about the prioritization of effort, right? So like in the first poll we had, we asked the question like, why haven't you optimized your PM? And a lot of people said, well, we don't have the resources or we don't have time. But if you take a step back and you look at all the work that we do in the plant, right? So all the work that we do in the plant, if you're in a highly reactive scenario, meaning like if you have a lot of failures, you're in the cycle of being reactive. So most of the work, and this bar graph illustrate the amount of work that's being done in a highly reactive scenario. So basically, most of the work that's being done, the equipment fails, and we send people or millwrights and technicians and operators to fix the equipment. So the reactive, the number of work order reactive are very high. So if you do a lot of reactive work, then you don't have enough time to do PM work, right? So you don't have enough time to monitor the assets. So if you don't have enough time to monitor the health of the assets, then you cannot build a backlog of corrective work order. Does that make sense? So highly reactive, not enough time to do PM, and if you don't have enough PM, you can't proactively monitor the health of the equipment, so you don't have good corrective work order in the backlog. So the idea is, how can we, improve the efficiency of the PM? That doesn't mean to do more PM, but to do PMs or to do inspections on equipment based on failure modes, for instance, so that you are more accurate and you can identify in advance more proactive work. So basically, your PMs are there to detect proactively a possible failure. And the only way you're going to be able to get out of that reactive silo is if you plan and schedule the work proactively. So those preventative maintenance or those inspection, they need to be able to provide you with the asset health. And then you build your corrective backlog. And as you correct those corrective work order, then your reactive is going to drop down. But if you take the sum of work that is being done, if you're highly reactive versus if you are doing more, condition-based monitoring and preventative maintenance and corrective work order, it's the same amount of work. The only thing is you're choosing when to do it versus the machine chooses for you. So, PM optimization is one technique to be able to provide that asset health information, but you absolutely need to get your planning and scheduling process in place in order to be successful. So, Some people will say, well, do you need to optimize all your PMs today, right? So that's a good question, right? So you need to prioritize because you don't have enough time to do everything at once. So the idea here is there's actually, I'm going to talk about two ways, but there's a third way that I'm going to talk about, right? So the first thing is you could refer to your criticality assessment and see and prioritize to optimize your asset strategies on your critical pieces of equipment. Meaning those critical assets will have a good asset strategy program. You'll be able to provide to monitor asset health, and that's going to gain uptime at the end of the day, which is great. So that's one way to do it. The other way to do it is focus your effort on bad actors. So focusing the effort on bad actor, if you have history of failure in your plant, you want to tackle the ones that have more unplanned downtime and review those PMs, right? So that can be done as well. So that's the other techniques that, or process we can do. The third one, which is not on that slide, is you could also prioritize based on the type of assets that you have. So let's say if you're in a refinery and you've got 600 pumps that are all not the same but similar, maybe you want to build a template of an optimized PM and assign that template to those 600 assets. That's going to help you, get up that faster. So though, depending on where you are today, maybe one of those three strategies would probably fit your need. So if you use those types of like the last one I mentioned, which is basically looking at what's the type of asset that I have, and basically defining a template or guidelines. Well, the first thing you need to do, regardless, is to define what is the common rules that you're gonna use to do PM optimization, right? So we call that a strategic session, or strategic session. So in that strategic session, you'll get people from different perspectives. So you get, for instance, operator, reliability engineers, or reliability specialists, as well as experienced trade people, right? So you assemble that team, and then you look at what are the most common components in the plants. So it could be motor, gearboxes, transmitter, valves, all that good stuff, right? So you define the types of asset that you have, and then you assign a strategy for these components in advance. So you standardize the different tasks, and then you define your strategy based on different criticality. So if you have a valve that is installed in a highly critical process loop, you might not have the same strategy for the same valve that might be in another loop of process that is non-critical, right? So you need to assign the right strategy for them. So the example here that I've got is a gearbox. You may have 600 or 500 gearbox at the site. The idea is, can I take one gearbox that is, and look at what is the typical failure mode of a gearbox. So I define the different failure modes that we see here in the up right corner. So those are all the different failure modes from the gearbox. And then we're going to decide as a group what is the task that we need to do. So for instance, in that example, you may do vibration analysis on the equipment. You could be checking for oil leaks. You could be checking for the level of oil in the side glass and so on and so forth. And then you're going to define, can I do that while the equipment is running or when it's down? Obviously, you want to focus whatever you can do safely when it's running. This is where you want to put your effort in, because then you're gaining uptime as you do that. Then you're going to define who in my organization is the most suited person to do it. Is it a predictive maintenance technician? Is it an operator? Is it a mechanic? Is it a technician? Right? And then, I was talking about criticality. So in this example, you've got three different criticality: A being the more critical piece of equipment, C being the less critical pieces of equipment. So maybe, in your strategy, you're going to say, well, for everything that's highly critical, I want to go there every 30 days and do vibration analysis, right? And check the oil leaks every 7 days. But maybe on a less critical piece of equipment that is identical, maybe you'll stretch that that frequency because the onset of the effect of failure is going to be lower, doesn't have the same effect on your overall equipment effectiveness, right? And then obviously define how much time will it take to do that task. So a task, so for each task, how much time are we expecting the technician to take or the operators to take? And what are the failure modes that they are addressing, right? So basically, this is what we're going to be doing. So, Johan, you want to talk about the details of the methodology?
Yes, absolutely. So after we've defined these guidelines, like Alain said, there is kind of a recipe or several recipes, of course, you could follow. You may know FMEA, RCMs, and PMO. So the objective of these slides, of course, in a couple minutes, is to go over some of the best practices with regards to PM optimization, not to go over the full scope of the project, but I want to give you some details. Before we move on, let's do a final poll here. I want to know, what are your preferred methodology to develop or optimize PMs? So this is a checkbox selection. So I'd love to know what you do if you optimize your PM, or if you've done it before, what methodology would you use? Okay, so I see a couple of RCM, FMEA, PMO. Okay, RCM and FMEA seems to be the biggest, bigger deal here. Very good. Very good. Some people have never done it. And so thank you if you're here to learn. That's really appreciated. Okay, I can see RCM, FMEA, PMO being the top ones. So of course, multiple recipes, different results, right? Typically, what we would say is that if you have highly critical, mission critical pieces of equipment with, you know, high lead time when it comes to getting the parts in stock, highly expensive parts to replace, of course, you'll choose RCM or FMEA. For other types of equipment, if you want something that is done quicker with a very high quality results, we'll use PMO. So the objective of the upcoming slides is to go over some of these rules. So the first thing we want to do when we do a PMO process is to deconstruct a piece of equipment. And, you know, not all pieces of equipment are very complex. Think about a pump. It's very simple. You've got a motor, a coupling, and a pump, and that's it. It's pretty much what it is, right? You can decide to attach the electrical cable or the breaker panel or the MCC if you want, and some piping, but it's very simple. Now take a if you go into a food and beverage company and you want a case packing machine, it's very complex with a lot of functional assemblies, a lot of components, and so the first thing you must do is to deconstruct that piece of equipment, because you don't want to miss any of these components, because if you're missing a component, well, you're missing some failure codes. And if you miss some failure codes, you miss opportunities to identify upcoming failures, right? So really, it's about going from bigger functional assemblies to components and then to failure modes, right? Here, I've given the example of a car, which is obviously very complex. And then what is the process? I'm going to give you 4 steps in there. So we'll start with a component, and we'll look at failure modes that are currently addressed by the existing PM program and failure modes that are not addressed by the existing PM program. We'll start with the part where we have failure modes and existing tasks, right? Again, PM optimization is based on something that already exists. The first thing we'll do is we'll remove some tasks. Now you can go back to the slides we talked about at the beginning of this presentation. Why would you remove tasks? It's because there's a lot of redundancy. There is a lot of non-value added tasks, old PMs, non-value-added PMs, etc. So really the first step in the PMO process is cleanup. We'll clean up the mess. The second step would be optimizing what's left. So optimizing what's left means a lot of things, right? Like Alain said, in the first place, one of the things we can do is to take tasks that are done on a down day and transform them into tasks we can do on the run so that we don't have to shut down the machine to do PM. And there's a lot of things we can do during that section. Here, I'm going to give you a couple of examples of things we can do to make life easier for a millwright or a technician when he's doing preventive maintenance activities. We can facilitate the access to identify issues, I don't know, on the coupling, for example. So you'll change the guard of a coupling, or you will add a window. You can use color codes for lubricants, hoses, power sources, fasteners, etc. You can use strobe lights to identify issues on belts, drive belts, or even couplings, the flex couplings, spider couplings, for example, and so on and so forth. The idea during that optimization process is to leverage, technologies that can be high-tech or very low-tech. If I look at this slide here, I'm like, this is pretty low-tech, pretty simple to put in place, like very simple color-coded gauges, for example, or color-coded torque seal, markers, Zert caps, with colors, not to mix lubricants, etc., etc. Right? Again, the idea is to make life easier when we're doing PM activities. Now that we've done the optimization, we'll add tasks and we'll mostly focus on the non-addressed failure modes. And I'm going to go back to that section here in a minute. So remember at the beginning of the presentation, we talked about overheat. We said overheat would have a high severity if it's not covered, and it has a median probability of occurrence, which in the end comes down to an unacceptable risk. So what are we going to do? We're going to measure the motor temperature with an infrared camera at a weekly frequency, and we'll ask the person who does it to write down the maximum temperature, and we don't want to exceed 165 degrees Fahrenheit. We need also to find the right person to do it. So that's why this PMO process, during that process, we need to involve the person at stake. There are lots of tasks that can be handed out to operators, or some tasks that we prefer the millwrights to do, or maybe the loop technician to do. And also, we want to discuss the right way to do things. So I deliberately said we want to use a thermal camera. It can be, a laser gun. Of course, we want to leverage the technologies that are, up to date in 2025. So it could be an entry-level camera or a very more advanced camera to capture the temperature of this motor. And finally, like I said earlier, we want to address the open failure modes. So here's an example of the way we do things. We use our software to do it, and I just want to take a couple minutes to explain to you how it works. So we've taken, I believe it's a gearbox here. So we have a list of failure modes of this gearbox here, and we'll look at levels of severity from 1 to 3 and levels of occurrence from 1 to 3. And we'll multiply the severity by the occurrence to give a risk penalty number. 3 times 1 equals 3, etc. Right? And what we'll do is that we'll look at what are the failure modes that are covered before the PMO exercise and what are the failure modes that are covered after, right? So you could say, yes, we're covering X amount of failure modes before, Y amount of failure modes after, and look at the difference and say, yes, it's great. But the way I like to look at things is with regards to risk. So you can assess the risk for each of the failure modes and it's done through that column. And you look at the risk before and the risk after. And here in this example, we've reduced the risk by 57%. By experience, I've done dozens of projects like this, and every time we run this matrix, the before and after ends up with a risk reduction of around 50 to 70%. It means that there are lots of failure modes that manufacturing sites are overlooking, and they are not taken into account. And in the end, this is what eats their lunch. So when you put in place these new PMs and you address those new failure modes, you're really reducing the risk of unplanned downtime, right? So that gives a really good vision of what to expect when you put those PM in place after, and what's going to be the effect on your unplanned downtime. Very interesting to do that exercise. Some considerations that you must have when you do these PMO projects is where are these new PMs going to reside? Is it going to be in my CMMS, an APM software, camera software, if you talk about thermal analysis, for example? Where are we going to display the trends? If we take pressure measurement, temperature measurement, etc. Again, CMMS, APM software, camera software. This is something that needs to be taken into account. Also, when it comes to create work orders, should it be manual, integrated with the APM software? Are we going to deploy those new PMs on paper, on tablets, etc., etc.? So lots of consideration. And of course, the most important is the training and the implementation. If we're building new PMs, for example, we're deploying drive belt deflection measurement, we need to train our millwrights on how to measure the deflection of a belt. That's pretty self-explanatory. Of course, when the tasks are done, we want to regroup them in routes. We're going to regroup by frequency, 30 days, done by a mechanic on a down day, etc., etc. It must follow a logical order. You must assess a total duration of routes. You must add photos, schematics if required, and parts and warehouse numbers, codes if required. Here, let's look at some what good looks like. Basically, these are a couple of PMs that we've found, or PMs that we've worked with. What we can see is what's the area, what's the asset, what's the component, what is the task, what are the instructions, what am I supposed to do, what are the failure modes that I'm supposed to look for while doing this PM. If I have to take a measurement, here's a place to write it down, and what is the maximum that I should be looking for. Okay, and again, a picture or attachments if needed. So really, if I would come to your manufacturing site and I would have a look at this, I would be, yes, good job. This is exactly what we consider a great PM. So execution is the key. Here, having the best maintenance strategy in the world is useless if no one is willing to execute it. You're doing PM optimization, you need to implement that. So again, whether it's through an APM software, your CMMS, pen and paper, whatever, you need to put that in place. It's a lot of effort, and most of you guys haven't done that because your lack of resources and lack of time. So if you do it, implement it as fast as possible after. It is the key. How to implement it? Ramp up routes for first iteration. Execute the routes with the PM, with your millwrights, your technicians at the first time. Get their feedback, right? Coordinate the execution in the CMMS. Train your staff. Install your visual indicators to facilitate the execution, right? So there's a lot of things to consider before implementing those new and optimized PMs. And finally, use digital tools, right? This is one of the items we said we would consider. There are tools out there. Maybe your CMMS can accommodate that. Maybe there's software that can accommodate that. Alain, you want to talk about a success story to finish?
I will, but just before we do that, I saw a question on the chat. I think it's relevant. Maybe you want to answer this question, Johan. Basically, on the RPM calculation that you presented before, why you don't consider the detection on the calculation? So RPN equals severity times occurrence times detection.
And this is a very valid point. In our methodology, we don't consider it, but this is definitely something that could be considered, the detectability. And will the PM you put in place be able to ensure 100% of detectability of this failure mode? Yes, absolutely, you're right. This is one recipe. The objective is to have a quick deployment, quick execution, and this is something we decided not to put in place in our recipe, but definitely a valid point.
Maybe I can just add to that, right? That's why the asset strategy session is so important, right? Because this is where we're going to be defining how we're going to be measuring RPN, right? So if detectability is one of the things you want to add to that calculation, we can certainly accommodate that. But this is where we absolutely need to get some alignment so that everybody, when they start doing PM optimization, we do it the same way, and we record that those risk factor consistently across the different assets, right? So it's all in the asset strategy session, I guess, that we would need to address those topics.
Good point.
So I'm going to talk about the result, an example of what was done at one of the facility that we worked in. I'm going to present this. This is already public knowledge because it was presented by someone that I would not mention at the CMVA conference in Atlanta, Canada, about, I would say, probably 6 years ago. So, but I thought it's still really relevant. So to the point that that Johan said earlier, it's all about how to integrate those PM optimizations, the optimized PM in the workflow, right? You can design the best preventive maintenance or the best asset strategy that you think of on a piece of equipment, but it's how efficient are you to implement those tasks, right? So really, it boils down to how you're going to be, putting that in the coordinating the work, scheduling the work, and making sure it gets executed, and that's where the payoff is going to come from, right? So, this example was where the company decided to put in place what they call a zero defect culture, and it's basically getting the operator involved in what they called reliability windows. So basically, they were stopping the equipment for cleaning and cleaning the equipment on a regular basis. So they thought about how can we optimize those downtime and make sure that we do inspection based on the PM optimization process. So they defined the asset strategy on each piece of equipment, and they basically trained their operators to do basic inspection and being able to identify failure in advance so we can better plan it and schedule it, right? And this is this is the bulk of what it does. So Johan covered the whole section about how you do that PM optimization, but then you got to figure out how you're going to implement those changes and making sure that you prevent those actions due to those new asset strategies in place, right? And this is the example of that plan. So basically, they had different downtimes. You can see the trends of downtimes over the years, right? So they were ramping up on a lot of downtimes. They did the PM optimization process. They implemented those changes, and right after, you would see that, the downtime went down very significantly. And, we had different conversation afterwards, and you know, this is sustainable in time. That's really the idea. So let's just get it done right once, but it's making sure it's sustainable in time, right? Then what does that translate into dollars and cents, right? So at the end of the day, you know, if you take an example, and that's, you know, even though this example doesn't relate to that that specific business case, I would say you need to understand what is the profit that you're making every minute or every hour at the plant site, right? So you got to define this, right? So in this example, it's $150 a minute of profit. You know, if you implement PM optimization, you could go up to, you know, in a similar example, up to $150,000 of profit because you reduce that downtime, right? And so, you know, so basically, making sure that you identify what's the payback, what's the return on investment, right, that you're doing. And typically for PM optimization process, your payback is probably, if you invest $1, you'll probably get $5 back after implementing the first year. And that's going to be consistently through time. So good example there.
Yes. Thank you, Alain. Thank you for your input. Really appreciate it. Thank you, everyone, for your participation and listening to that. I hope it was insightful. And now is the time. If you have questions, we have a couple minutes left. And if you don't mind,
You can use the chat or ask questions.